Aishwarya, are you here?
Hello, can I be heard?
Yes, I think you're heard. Okay, awesome. Aishwarya, welcome to the stage. I'm gonna come back in a few minutes. Take it away.
All right, great. Hi, everyone. I'm Aishwarya. Really excited to be able to speak today. I'm a machine learning engineer at Chime, which is a fintech company that aims to address everyday people's needs with free and helpful financial services. I'm going to be talking about some data engineering practices that support our data science developer experience, particularly when it comes to feature engineering. So I'll explain a bit of context to break this down. I'll get into high-level infrastructure and the interfaces through which data scientists can leverage that infrastructure. And then at the end, I'll briefly touch on some common feature engineering challenges that we have to keep in mind when solving these problems. So being a fintech, we have lots of use cases for machine learning. Obviously, that includes fraud detection. So examples can include payments between users, mobile check deposits, and unauthorized account logins. And many of our use cases rely on near real-time inference because of the very strict latency requirements, being able to respond as quickly as possible. So for example, in terms of unauthorized account access, we want to act as soon as possible before a malicious actor can do harm by accessing the user's funds. And Chime handles a lot of data, so that makes low latency inference serving challenges grow even more as our user base continues to grow and we have more and more data to store internally. So when we're developing models for some of these use cases, we generally have three types of features that the models depend on. So going from left to right, batch features, which are calculated over a window of historical data, typically at a regular cadence. And examples like a feature calculated of total withdrawals over the past week for a user and updated on a daily basis. Near real-time features, which are computed also over a window of time, but have typically lower latency because we have streaming pipelines and streaming ingestion to support their computation. And that could be a feature like the past 5 minutes of transactions for a given user. And then, of course, real-time features, self-explanatory. They're available right away. We typically get them from whatever caller service in the payload request upon model invocation. So with that information in mind, as a data scientist or MLE, I really care about a few things. I want fast feature lookup to serve my real-time models. I want data quality checks in my ingestion infrastructure so that I'm aware of feature quality impacting my model's performance. And I want interfaces to be able to define my feature logic and not have to worry about, do I have parity between my development and production environments? And I want to make sure, and this is easier said than done, that my features generated are correct, especially this is tricky with data that's always evolving over time, which we'll discuss more about a bit later. We can translate those needs into some technical requirements for our infrastructure to support that perspective of data scientists and MLE work. I'm going to need an online feature store to serve my real-time models with low latency, separate from an offline or at least offline computation of features. That might be sufficient for batch models and training pipelines, but it's not good enough for our real-time use cases where we have to serve features as quickly as possible and do inference in milliseconds. So secondly, a feature library will help us consolidate subject matter expertise and define features in one place so that anyone in our company or in our organization can reuse them to create their own model or do data analysis. We also need to combat training serving skew, which introduces feature disparity and obviously model performance degradation between training and production inference serving. We'd also want to eliminate feature mismatch or the case of feature mismatch because of any ad hoc feature serving logic or trying to re-implement feature logic in different cases or different environments and reinvent the wheel when we can just all have it consolidated in one place. And finally, when it comes to feature serving, I just want to make sure that I'm computing correct point in time feature data. Again, that's tricky when data is always updating over time and you have variable system lag to deal with. So to help meet some of those requirements, at a high level, our platform supports different infra for batch and real-time, near real-time feature serving. On the right side, we have like Kinesis streams and glue jobs to execute transformations in a Spark SQL environment. And this supports our near real-time features for more efficient parallel processing of large workloads. And we can maintain fresher features when it comes to near real-time processing. And the data is written to our online store, so models can just query those pre-computed features through more performant reads. On the bottom left for batch features, we can compute features on demand, or we can read them in an offline store if we have since we have less strict latency requirements than we do with real time. We don't always want to deploy features generated to use our real-time ingestion infra with like these kinesis streams and glue jobs because it's generally more expensive to use those resources. So it's only beneficial if that low latency is make or break for your model performance. So a model that generates a batch of predictions once per day might not really need it. And then there's interfaces that data scientists commonly interact with to leverage that infrastructure. So on the right side, users define feature logic in our library to consolidate query logic, ingest, and that can also help us configure ingestion jobs, configurations, etc. On the left side, users specify which features to use in model development when they're actually training a model. So I'm going to go in a little more detail of how these interfaces enable data scientists during feature development. In feature library on the right-hand side, when users define their features, they can specify details about their feature like metadata, along with the actual SQL query logic for the features. We can detail the windows of time that we want the feature to be computed over and like the cadence at which we want the job to be kicked off so that we can run all those transformations and then update the value in feature store. Once we define this feature information, CI jobs help us generate like what configuration we need for glue jobs, what configuration we need for data quality checks, etc. And data scientists are also able to update those data quality checks via config and set up like what kind of alerts they want in PagerDuty and how they want to conduct checks in their SQL query logic. So the interface enables them to specify what features to use, and the logic for those features that are defined in our feature library is reused during model development on the left-hand side and lets us make sure we maintain the same logic regardless of the environment we're doing feature computation in. So data quality checks enable data scientists to specify checks at different points of the ingestion flow. We can check before data transformation even occurs to make sure our source data is even good quality and there's no corruption or missing data. That can save us money before we kick off a pipeline that's going to fail or error out anyways. And then, of course, checks after we do the transformations to make sure we didn't lose data or, again, that it was corrupted. And then after data is loaded to our sink, we can check it again, or like a data quality check would be useful again to make sure that downstream consumers, again, are not receiving corrupted data. Those downstream consumers being like real-time models that rely on the features ultimately landing in feature store. So we can check null rates, duplicates, freshness, etc., all the usual stuff. So I'll close out then briefly by highlighting some of the challenges we have to address in feature engineering. So feature availability lag, that's a challenge that can introduce feature disparity and make point-in-time feature generation trickier. Just to define again, like point-in-time feature generation is basically making sure like a sample at a given timestamp, when we generate features for it, we are only joining records from different sources using data that's available at or before the prediction timestamp. If you include data after, then that constitutes data leakage from like future data values and will give you inaccurate performance of your model or inconsistent between training and deployment. So in addition to this, we also see delay from source data availability, so like just being loaded and available in the source storage location, and then also delay due to processing itself. So we have to be able to account for these delays at training and inference serving when essentially data scientists actually have to configure the features for model development on the left-hand side here or in feature library on the right-hand side here. We essentially parameterize that so that if a feature, say, is served, it might be delayed by 5 minutes because of lag at inference time. That means the feature is only based on data available up to 5 minutes before the prediction is generated. So at training time, you also have to make sure you're only creating the feature based on data up to 5 minutes before the timestamp. And by timestamp, I mean like the point in time the data was became available to do feature processing in the first place. So to close out, I hope that you had some insights from this quick talk, namely more understanding of the infrastructure requirements for both batch feature processing and real-time feature processing to like maintain model performance in production, and also like how we can expose unified frameworks for data scientists despite this divergence in the underlying infrastructure. So yeah, thank you everyone for listening.
Thank you, Aishwarya. We do have a couple of questions. I know we don't have too much time for questions, but if it's okay,
Sure.
I want to ask them. Okay, so Rohan here says, how do you handle feature drift for features that do change over time?
Features that do change over time. So that is like a whole presentation in of itself, probably with observability, which I'm sure some people are talking about. Essentially, like you need to build out monitoring capabilities for your models. You can see the distribution of like the predictions that the model is generating, and that can give you insight into how some of your features are changing. And you can also, another way is tracking like feature lineage. So being able to see like upstream sources for your features and seeing any changes in those that might impact the features that your model actually relies on. So that can indicate to you whether there's potentially feature drift down the line. Again, upstream changes can impact that. And yeah, Datadog monitoring essentially is like the feature you would need to make sure to build out for your models, and also for your blinds that do data ingestion for, in my diagram where I showed like near real-time feature ingestion. Yeah.
Yes. How do you pack your ML models for serving on Bedrock? And how would you specify the output collections on Dynamo that
Serving
the
on
model should write
Bedrock.
to?
So we're on Bedrock necessarily, but essentially, like we are using containers to serve model, and we're able to duplicate what logic we have for our workflows for inference and for training in our container environment for real-time or batch. We configure those beforehand, and we can generate model artifacts to store storage location and be able to basically read that in our actual inference environment. From that storage location, we basically read like, okay, what version, to make sure we have the correct artifact to execute predictions in production. I'm not sure if that answers the question, but yeah.
If not, they can find you in the chat. Thank you very much, Aishwarya.